Hello and welcome to your third fully vodcasted lecture this semester. If you're watching from the regularly scheduled classroom, then this is Friday the 7th and you're totally jazzed because it's Friday. And for me, I'm totally jazzed for a completely different reason. That is because you guys seriously rock my world. 84% average on the exam. That is just outstanding, phenomenal, supercalifragilisticexpialidocious. I have never seen an average like that. So you need to be thinking about just how it is that we want to celebrate having achieved this. So by the time I get back, I'm hoping that you'll have some things in mind as to a good idea for a celebration. And I'm just super excited and very proud of your efforts on that. We do have some getting down to business announcements, however. We do need to get homework number 3 done for Tuesday, February the 11th. Also, if your groups could start thinking about hypotheses and sending drafts of hypotheses my way, I would love to receive some of those early in the week, next week, but certainly by the end of the week. In lab, we're going to be working on getting that unknown press release done for the end of the week. That'll be due on Thursday the 13th. And also on that same Thursday, if you would like to, you can build a Winogradsky column. Harley came and asked me the other day about whether or not the Winogradsky column is essential because, of course, many of the lakes and rivers and streams around town are frozen. No, absolutely not. This is not an essential part of the class in any way, shape, or form. It is, however, worth extra credit. So if you're getting jazzed about some extra credit and you have a place to go that you can get some mud and water, then more power to you, and we would love to give you some extra credit for it. So without further ado, I want to tell you a little bit more about the story that we were telling last time. Remember how we had talked about endocytosis, the two types of endocytosis being phagocytosis, or the big gulp, that is bringing in a large region of the fluid-filled exterior, versus pinocytosis, or just the little pinching off of a small region. So these both were methods of endocytosis. Let's contrast those then with exocytosis, which is the opposite, which is releasing contents from the cell into the exterior. So exocytosis, sort of the opposite of endocytosis, and seeing the release of contents through that mechanism. This then wraps up that particular concept, and it makes me totally stoked because it means we now get to talk about my favorite eukaryotic cellular structure, the flagella. Flagella are so amazing. Now, this is true of bacterial and archaeal flagella as well, but eukaryotic flagella are very different than bacterial and archaeal flagella. Remember with bacteria and archaea how they moved like propellers, so they can move either, a clockwise motion or counterclockwise motion like a propeller. But this is very different from a eukaryotic flagellum. A eukaryotic flagellum moves like a whip, so it kind of has this whip-like structure to it. It also is very different in that the prokaryotic flagellum is external to the cell. Remember how we had the basal body, the hook, and the filament? Well, we don't see that in the eukaryotic cell. In the eukaryotic cell, we see that, in fact, this is weird, the cytoplasmic membrane literally coats and covers the entirety of the flagellum. So the flagellum is actually membrane bound. So while it is a structure that looks like it projects out of the cell, it doesn't. It's actually covered by cytoplasmic membrane. So this is very different. The next thing that's different is the ultrastructure. If you think back to the filament of the prokaryotic flagellum, it was made of the protein flagellum in a helical pattern. However, within the eukaryotic cell, the center or core or ultrastructure of the flagellum is made of microtubules. Remember, that's the largest structural element of the cytoskeleton. So think about a region of the cytoskeleton, boom, projecting out and being then surrounded by cytoplasmic membrane. And that's what we have with regards to the eukaryotic flagellum. So looking at the ultrastructure a little bit here, we can see that we have microtubules in doublets. And in fact, at the center, there is a doublet, and then around it, it's surrounded by 9 doublets. So this is something that we call the 9+2 pattern. The 9+2 pattern is a very fitting description of the eukaryotic flagellum. If you cross-section it and you look on it end on, we see something that looks just like this. And I hate to pick on James in 2 vodcasts in a row, but we all know he loves that unicycle, and this is very much like the unicycle wheel. And in fact, the people who discovered it thought the same thing. They named this with terms like, this is the spoke head, and this is the radial spoke. So these terms also very fitting of the kind of ultrastructure that looks very much like a bicycle tire. Now remember that that's looking end on. If we kind of look from the side a little bit, we can see the cytoplasmic membrane extending around the microtubule ultrastructure there. Remember that the way that eukaryotic flagella move is also very different. Rather than moving like propellers, they move like whips. So they can move in two different ways. They can move like a whip from the base to the tip, or they can move like a whip from the tip to the base. So we can either get this motion where it moves from the base to the tip and it pushes the cell along, or it can move from the tip to the base and it pulls the cell along. You got it? Like the base to the tip, tip to the base, base to the tip, tip to the base. So this is the motion that we're going to be looking for from the eukaryotic flagellum, and that dictates whether it's pushed or pulled. Unless you have a very special situation in which you have a flagellum that has little flimmer filaments that project out from it. These little flimmer filaments are increasing the surface area of the flagellum, but they're also changing the way in which it moves. So a flagellum with flimmer filaments on it, instead of being pushed when it moves from the base to the tip, it's pulled when it moves from the base to the tip. So it's the reverse of those flagella that do not have the flimmer filaments. So flagella without flimmer filaments are called whiplash flagella. Flagella with flimmer filaments are called tinsel flagella. Try saying that 3 times fast. So sometimes a flagellum may have those flimmer filaments and sometimes it does not. So without further ado, I imagine you are all prepped to watch the epic flagella dance. The epic flagella dance was made by a student of mine who is now an optometrist. His name is Zach. You'll see him in the middle. Zach's work on this video was epic because it was on a Friday that I said to the class, man, the flagella movement would sure make a good dance. And it was on Monday that Zach handed me a DVD.
Yo, yo, yo! Introducing Endocytotic Cat, Mac Master Cilia, and Hypotonic Z.
Yo, all you listen, we're here to tell you what you're missing. We rapping about a topic so small it's microscopic. Projections out of the cell, move so fast you just can't tell. Sways like a whip from the base to the tip. We talking about the flagella, who's one cool fella. So get down with your microscope, and what you'll find is something real dope, working on your sexy mind.
Hey young fellas, can get down with my flagella. Wave your arm around like you just got a yella. Getting all funky in my crazy microscopic. My pen's so rad you just can't stop it. Gotta get a stroke, you gotta wave. Moving it all around like a crazy cell rave. My cells ain't lame, I never been tame. You just go insane in your membrane.
Hey, give me your attention. I got something else to mention about something a little smaller, but he's still a big baller. This guy moves with a stroke, really ain't a joke. Moves particles along the cell, in case you couldn't tell. This gangster's a Cilia, best make yourself familiar.
Short little Cilia, you know I still feel ya. Tight little monster raging like Godzilla. Rage like Godzilla. Rage like Godzilla. It's in your membrane.
So here's the thing, and don't tell Zach I said this, but you know, his video's getting a little old school. And you know, quite honestly, you guys have some pretty good music skills out there. And here's what I would say. We need to make like a brand new trendy, like hipster version of the flagella dance and like send it to Zach, because that would be way cool. So I'm looking forward to somebody submitting. And let me just tell you, that is epic extra credit. So do it. And while you're thinking about it, I want to talk about Cilia. Cilia are another structure similar to flagella. That is, their ultrastructure is actually quite similar, but they're much shorter than flagella, and the motion that they have is much different. In fact, I'm going to pick on Rudy just a little bit to talk about the motion of the cilia, because I know Rudy is a pretty BA swimmer. He's on the swim team, and so he probably remembers the way back to when you were like 1 year old and you were learning how to swim, and you were probably learning something called the elementary backstroke. And you remember the elementary backstroke? It had like this cocking stroke that's like an effect, that's like a recovery stroke, and then you had the like effective pushing down stroke. So you kind of do that cock, and then you'd have like the push down. And this is how cilia move. That is, they have an effective stroke where they're pushing down like an oar, and then they have the cocking stroke where it bends up and then repositions for the next stroke. So this is how they move. But what's really interesting about cilia is that they don't all move together. Instead, in fact, one might be in a cocking stroke while the other one might be in an effective stroke. So it just is variant across the group of cilia. Now, the purpose of cilia varies. In some cells, it is used for motility, but in others, it's actually used to move other things across the surface of the cell. So, for example, one of the types of ciliophora, called stentor, has a very large buccal cavity. That is, it has a cytosome, or a mouth, and it uses the cilia that line the mouth to move food into the mouth. Right? It works really well. So this is the last of the eukaryotic structures that we're going to talk about, but I want to encourage you to contrast and compare eukaryotic and prokaryotic structures. So in fact, I'm going to begin a table, and I'm going to go ahead and put in this table the structures, cellular structures. So the first column in this table will be cellular structures. And you're going to fill this table in. I'm just going to do the first entry for you, and you guys are going to run with it and do more. And then your next column will be present in bacteria. That is this something that we find in bacteria and archaea? Question mark. And then present in eukaryotes. Question mark. So I'm sure that flagella is hot on your mind. So we could say flagella would be the first cellular structure that we would think about. Present in bacteria? Sometimes, if they're motile. Same thing, present in eukaryotes? Well, yeah, sometimes if they're motile. But then we would want to contrast their structure. We would want to say that in bacteria, they move like propellers. Whereas in eukaryotes, they move like whips. In bacteria, they have a basal body, a hook, and a filament. Whereas in eukaryotes, they have a 9+2 microtubule doublet pattern. Now you could keep on going with this contrast and keep writing things that differ between the two. And I want to encourage you to do that. I want you to keep making entries in this table. Maybe your next entry would be ribosomes, and you would talk about whether they're present in bacteria or present in eukaryotes and contrast them in both. So that's your task should you choose to accept it. I'm going to go on and start to talk about transport systems and about nutrition within all types of cells.